Okay, hi everyone. Today I'm going to talk about the organization I work for, who we are, what we do, how we do things, some of the challenges we are facing today. We also are going to explain why we started thinking about using OpenStack in our environment. We're going to explain how we deploy OpenStack, the things we like, a couple of use cases, and after that, how we see our future with OpenStack. So my name is Manuel Sopena Ballesteros. I'm a systems engineer at Garvan Institute of Medical Research. These are my IRC nickname and my email addresses in case you want to contact me after the summit. So I work for Garvan Institute of Medical Research. Garvan, we also call ourselves a medical-driven, information-driven medical research center. So at Garvan, what we do is we research about rare diseases. We have 5 different areas, and we host around 80 bioinformaticians. If a bioinformatician is basically a data scientist, but their domain expertise is biology data. We also collaborate with many other entities in the world. For example, in my case, we are now in a project with Intel. We also work with Dell. We compute locally. We compute in AWS, Google Cloud, and we use the NCI National Computing Infrastructure in Canberra. So most of the research we do at Garvan is based on genomics information. So because of that, we host the 5th biggest sequencing lab in the world. And in those labs, we have machines like those ones. So how it works is you load the biological information into the machine through a sample that normally comes from blood. And that machine translates that information into digital data, which is then stored into a different place. And that's the starting point for our bioinformaticians to start running their workflows and pipelines. Okay. Within Garvan, I'm a member of KCCG group, which stands for Kinghorn Cancer for Clinical Genomics. And within the KCCG group, I'm a member of the TIES team. And what we do there is we research about technologies that might help our end users to do their jobs easier. So basically, we try to abstract the technical part of their jobs in order so they can focus on the real deal they have to, the real challenges they have to deal every day. So in Garvan, right now, we operate through HPC. So we have 2 types of nodes. Some nodes are virtual machines, we call them the login nodes. The other type of nodes are compute nodes on bare metal provisioning. We install everything using ROX cluster. And on top of that, we build a software of different services using Ansible. And for storage, we use a proprietary high-performance distributed storage. So right now, we have seen HPC to be quite efficient for us. The reason is because HPC can manage the resources quite efficiently. The reason is on HPC, the users log into a login node. After that, they submit jobs to the job scheduler. The job scheduler coordinates with a resource manager who has an overview of the resources on the entire cluster. If the cluster has enough resources for your job will kick in and start running. Otherwise, we'll be placing a queue and we'll be waiting there till the right moment to get executed. Also, HPC provides a great performance because it runs in bare metal. On the other hand, it's hard for us to prototype environments on HPC because HPC only gives us a unified environment. So if you need to add new tools to our HPC system, basically we need to adopt those tools to the HPC environment, which means We need to recompile libraries, dependencies, etc., etc. On top of that, we delegate these operations to the end users, and we sometimes find it's quite challenging for them. On the other hand, the end users don't have root access, so they have to mount and build everything by themselves, put it into their home folders, and then run it from there. So I explained who we are, how we work, and now I want to show you a couple of challenges we are facing right now. So this graph shows the cost to sequence a genome. So if you can see, the first genome was sequenced in 2001 with a cost of $100 million US, and different advantages in sequencing genomics technology has driven down the cost to a point where today we can sequence a genome for less than $1,000 US. So because of that, many people is interested to work about genomic information because we feel it has a lot of potential for the future. And because of that, more and more people has access to this type of technology. We see in our field, which is called computational genomics, is heavily disrupted by new applications that is appearing from other research groups or private companies. Another challenge I wanted to mention is if you see the gap between the Moore's law and the cost of sequencing, the bigger that gap is, that means the difficulty is for us to compute the information we generate. The reason is with each new version of our instruments, we not just generate more data, but we generate it quickly. So the time we need to process the genome samples is shorter. Another challenge we face in the recent past is this one. So we are collaborating with the government of New South Wales in order to provide a tool that can store and provide an analytics platform for around genomics information. So we find, because of that, we started a partnership with Genomics England, who are trying to do the same, and they started building a tool called OpenCGA. So part of that partnership was to bring that tool into our infrastructure. But we found a huge number of limitations because, first thing, this type of tools doesn't really fit on a HPC, because on HPC, when you start a job, your job already has an expiration date. It has to start and it has to finish at a certain point of time. But these tools are meant to be built, installed, and run 24/7. They provide the storage layer, business logic layer. It provides a REST API where the client needs to query into it. So to summarize, we have two challenges. One is scalability in terms of the data we manage, and the second one is we need to find a way to prototype faster in order to adapt quickly and provide environments for the new tools that are appearing in the market. Today, I'm just going to focus on the second point. I'm not going to talk about scalability, okay? So because of all this, we started thinking about OpenStack. We also know about many different successful use cases in our field, which is research, using OpenStack, so we decided to give it a go. So just to summarize, I believe many people might give you a different idea of what OpenStack is, depending on how they use it. In our case, we use OpenStack as a platform, as a service, and which means that we put OpenStack on our infrastructure, so we can ask OpenStack to couple different type of resources and provide this in a different media and a different environment. So what do I mean with resources? What I mean is CPU, memory, storage, and networking. When I talk about media, what I mean is I want to be able to provide those resources on bare metal, virtual machines, or containers. And what I mean with environment is I want to be able to provide the software that sits between my user code and my resources be flexible in that way. For example, I'm talking about the operating system. So if I have a user that needs to run a tool and that tool has been tested on Ubuntu 12, then I need to be able to provide that environment for the user instead of asking him to make that tool to run on what we already have. So this is a list of the features we want to get benefit from OpenStack. So granular resource allocation, which means we want to be able to take physical hardware and break it into different pieces so we can reutilize and do more things with less. We also want to be able to deploy bare metal VMs and containers. We want to use multi-tenancy. We're not using multi-tenancy yet because we don't have enough resources, but in the future, once we expand our OpenStack cluster, our idea is to create projects with quotas and give our users access into it so they will be free and self-efficient to build their own environments. We also like OpenStack because it gives us a unified set of user interface in order to manage different resources. In the past, we used to, for example, if we want to set up a network, we have to log into a switch or a router or a firewall. If we want to allocate storage, we have to go to the front end of the storage system, etc. With OpenStack, we can do all those things in a simplified way. We also want to use shared storage and distributed storage because we work with large data sets. So this gives us a lot of flexibility. We also think that the open source community is driving most of the innovation nowadays. So we want to be close to them. We also want to run on commodity hardware because we have teams doing research on machine learning and other type of fields in IT. So in the future, we might need to be able to support GPU clusters. Very soon, we're going to receive FPUs for some of the projects we are working, etc., etc. And plus, we think that using open source tools, we might get into reducing costs. So OpenStack is an umbrella of different projects, right? Different projects might give you different functionalities. So you basically build OpenStack in the way you want it to run, depends on your needs. In our case, we are very keen to manage different type of resources. For example, we are very keen to start using soon because we want to manage containers through OpenStack to make our lives easier. We also want to be able to do bare metal provisioning. Neutron is one of the projects that we get most benefit. The reason is we, the DICE team, we have our own physical network, but it's quite limited. So if we want to do things differently, we need to coordinate with our IT department. Now, by using Neutron, we could virtualize the whole network infrastructure, which gives us all the flexibility we needed to do in order to prototype. With Glance, I said before that I want to be able to provide different environments for our users. So that is where Glance kicks in. With Glance, you can store your different images, and basically you can give that flexibility to the user. So you can upload CentOS, Ubuntu, different versions. Apparently, you can also run Windows. We haven't tried that yet, but it's something we are looking into it. With Cinda, give us a lot of flexibility because on OpenStack, you can do things like go to the command line, OpenStack, volume, create, size, volume name. That's it. Your volume is created, and you want to attach it to a VM. You just do OpenStack server at volume, server name, volume name. That's it. Block storage attached into your environment. I'm going to talk about Manila afterwards. We have a use case with that. And also Ceph. Ceph is the distributed storage, which we think is a good way to scale in and scale out according to our needs. So how do we deploy OpenStack? We started from a very basic environment. We use what is called PackStack, which is a RDO Red Hat distribution of OpenStack. So with PackStack, we took basically one compute node, and we create within that compute node the whole OpenStack environment, which means the control node that makes sure OpenStack, the different services of OpenStack are coordinating, but also the computing. So we play with OpenStack, we like it, we wanted to go to the next stage, which is deploy OpenStack on a small cluster. Now, the challenge for us here was introduce OpenStack on our infrastructure means taking resources from HPC. But unfortunately, our HPC system works at high capacity every time. So how can we do this efficiency and reduce the impact of our current environment? So we decided to deploy OpenStack on the same way we deployed HPC, which means install the control nodes on VMware cluster, and then the computing will be on bare metal. So the next step was to use TripleO because the OpenStack project to provisioning OpenStack on production, but we failed. We failed basically because we couldn't make TripleO to be installed on the VMware cluster. So we thought about it, and then we decided to go through containers because you run with containers means you can run anywhere. So we went through the OpenStack documentation, and we found the Collab project, which means what they are trying to do is to deploy OpenStack on containers, which is the same idea we were after. Not only that, they also try to reduce the complexity of deploying OpenStack. So the Collab project has 3 branches. One is the Colla itself, which are the Docker containers for different services of OpenStack. The second one is Colla Ansible, which is a set of Ansible playbooks that will deploy OpenStack on containers. And the third one is Colla Kubernetes, which deploys OpenStack on containers on a Kubernetes cluster. We found it very easy, the installation. Well, we went through the documentation, we ran a couple of issues, but we connected with the user community of OpenStack, and they were very helpful. So we really like this Collab project. So for the installation, it's very easy. You just start with a deployment node. On that deployment node, you put the Ansible. You make sure that that deployment node can talk to the rest of your infrastructure. Then you install call Ansible, which is you can install it through pip. You run pip install call Ansible, that's it. Then there is 2 configuration files you need to configure. One is to tell your cluster which physical NIC talks to which OpenStack network. And the second configuration file is just the Ansible inventory file, where you tell call Ansible which node has each role on OpenStack. Some people just want to take the containers and do the deployment by themselves. If you are thinking to go through that path, those are the links where you can take the Jinja 2 templates in order to create the Docker files to deploy your own images. So this is our current test environment. So we took our VMware cluster, we put the 2 VMs there, one with Colla deployment VM and the other one with the OpenStack, the controller, the control plane from OpenStack, which involves the security with Keystone, the Neutron server, etc., etc. And all the computing, we put it on bare metal machines. And we also leveraged the storage to a Ceph cluster with only 2 compute nodes. So what did we learn through this process? The first thing, if you want OpenStack to talk to other internal services in your environment, you need to make sure that the external gateway can route to those services. Because OpenStack only talks to the external world through this external gateway. Then another thing is, there are 2 networks on OpenStack that needs communication to the outside world. One is the admin network, and the other one is the provider or external network. So make sure you have a gateway for those links. Also, make sure you always use stable releases, because otherwise you might end up in a lot of trouble. I'm talking about the Docker containers, the Cola containers, and the Ansible playbooks. And also, once you are troubleshooting OpenStack, make sure you know which services rely on which. For example, before I was building an environment, I was playing with it. I was using a test dataset. The tests were successful, so I wanted to test the production dataset. I was connecting the storage through a Manila shared volume. I wanted to extend the volume. I ran into a problem. I went to Manila logs. I was running short of quota. I increased the quota in Manila. I did a second attempt. I failed again. And now the Manila logs didn't say anything. So going through the documentation, then I realized that the Manila leveraged the building the volumes using Cinda, which is the block storage project. So what I did was I went to the Cinda logs, and then the Cinda logs told me the real problem, which I got it fixed, and then everything keeps working. So make sure the dependency between the projects you deploy in order to troubleshoot any issue. The second thing is because our control nodes were running on VMware. VMware by default tries to block any traffic from any MAC address that doesn't know. So because VMware didn't know about our OpenStack infrastructure, basically all our instances didn't have communication to the outside world. If you want to fix that, you need to go to the VMware distributed switches and then enable the promiscuous mode, and then the forge transmits. Now I'm going to talk about a couple of use cases. So the first use case is how we deployed OpenCGA. So because this is all about prototyping, we virtualize the whole infrastructure. So we create a virtual network, we create a thick VM, we install OpenCGA there. OpenCGA talks through a big data stack with Hadoop and HBase. So we create another VM for the big data deployment. We use Apache Embody for that. Then we deploy another VMs for the Hadoop. We deploy the Hadoop system using Embody, and then finally we connect OpenCGA to the cluster. The second use case is a project we are currently working with Intel. So in this project, we are trying to create a test environment for GATK4. GATK is a tool. It's based on Genomics Analytics Toolkit. It's one of the references to analyze genomics information. And is currently part of our production pipeline. We run version 3, and one of the advantages of the GATK4 is that you can use an Apache Spark to do part of your computing. So we wanted to play with it as well. So we did the same thing. We virtualized the whole infrastructure. We use one thick VM to run GATK, another several thick VMs to run Spark workers, and for the master, we run a small VM. Now, because all the nodes in GATK needs to have access to the input files, instead of copying the files from one compute node to another, we just create a Manila shared volume, and we connect the different clients into it to solve that problem. Things we want to do with OpenStack. So we know we like the technology. We would like to go forward with it. Now, what we are trying to do is to improve the performance. Because we are using OpenStack to run a lot of analytics workloads, we want to reduce the latency of the network. We have different ideas about how to do that. Then we want to do the integration with Ironic for bare metal provisioning, HIT for orchestration, and Designate for the DNS integration. We also want to integrate it with our local Active Directory. We also want to run managed containers through OpenStack. So Soon and Carrier are two projects that we are very keen to start working on. And we run Ceph, but we found a few limitations deploying Ceph through Call Ansible. So what we're going to try to do is deploy Ceph the way we want, because we Our Ceph cluster is called all flash. It runs all on NVMe, and to do that, you need to pin the CPU on the NUMA nodes to talk to the right NVMe disk, so to improve performance. And now, if you want to start using OpenStack, I would recommend you to use Cola, because the philosophy is, I think, is really good for start working with this type of technologies. They try to simplify everything. It's highly opinionated, but I think it's a good starting point. They try to do the same with the documentation. The documentation is short, it's very well written. It gives you the steps to keep going. If during the installation process you are stuck or you have any issue, just go to the community. They are very happy to help. There are two IRC channels, OpenStack and OpenStack Cola. They have the Slack channel as well, and then the OpenStack user mailing list. And just to finish, I want to say thank you to the OpenStack community, because they have been very close to us during the whole process of deployment. Say thank you to Dr. Warren Kaplan, who is the supervisor of the DICE team, Derek Ling, who always helped me with the provisioning and the configuration of the networking, and Dimitri, the Garvan, and Shane Husson, who are always giving me new use cases to run OpenStack. And now, if you have any questions or feedback or sorry.
So what storage are you using behind your Cinder driver?
We use Ceph.
Okay, you were saying that you were using Cinder to provision storage to Manila at one point?
Yes. So we use...
Oh, so you're using Ceph?
Yes, we're using Ceph for that, yes.
Okay.
We are also planning to use, well, that's not Ceph, because we also run a lot of we want to run analytics pipelines. We also want to use ephemeral disks using the local storage on the compute nodes.
Okay, is any of that local storage flash? Are you using any flash in this solution at all?
Yes. So Ceph is based on flash, yes.
How far are you in the new system? So, the plan, do you have any plans to get rid of the legacy HPC and move everything to OpenStack, or are you going to keep the two systems together for how long?
Well, we will keep the system together for a while, because our production pipelines run on HPC. But ideally, in order to simplify our work, we would like to take this opportunity to deploy OpenHPC and do the integration with OpenStack. Yeah.
I've got a question about Ceph. You mentioned that you're running Ceph on NVMEs. I'm wondering what performance you're getting in terms of megabytes or gigabytes per second, as well as IOPS.
Okay, IOPS, I don't remember. Megabytes per second, we are getting, well, by the way, we deploy Ceph using Cola and Ansible, and we know it's not the best way to deploy it. But from the numbers we got, we get, I think, 2.5 gigabytes per second.
Okay, another question I have is, you mentioned that you'd like to optimize performance of the cluster. What are the performance bottlenecks that you're hitting? Which ones affect you the most?
Well, for example, if you run on NUMA nodes, you want to pin your CPUs your virtual CPUs to the physical CPUs. We want to address that. In terms of networking, we want to reduce the latency, so we are thinking to use either sROV or OBS on DPDK to bring the OBS process into the user kernel, into the user space. Or if that's not enough, then we might just get rid of the software-defined network and then start using the provider networks. So the VMs can use the physical network infrastructure. And then in terms of performance, storage, we also want to be able to make OpenStack, make Nova to use the ephemeral disks on local storage on the same compute node.
So why do you need the ephemeral disk if you already have all the Ceph infrastructure on NVMe? Because I mean, do you have any much increase of performances using ephemeral afterwards?
No, basically it's to provide, imagine that we get a tool that needs runs on HDFS, right? So what's the point of deploying HDFS? You can deploy HDFS through Manila, but if you can give a better approach in terms of hardware and software on the environment you are running, we think it's better. Plus, with ephemeral, yes, you lose the storage if the nodes goes down, but we don't care. If we run about HDFS, you have already a distributed file system there. So
yeah, all right, thank you.
You mentioned that you're actually using BRM to actually build environments so people can build the environments that suit their application and they install on top of that early on in the thing.
Sorry, can you repeat?
So you mentioned that you wanted to use bare metal so that people could build the environments that suit their application.
Yes.
How do you control that from a security perspective?
To be honest, we haven't think about that. But the environment we run is quite restricted. It's quite restricted. So I believe we will address it the same way we manage the security on HPC, which is also bare metal.
So you'd have constraints about what they could put in there?
Yes, of course. So we want to get the max performance we want to get from the virtualized environment. Also, we think running containers through Zoom might give us an advantage. We still don't know because we haven't played with it, but that's our hope. Then having the flexibility of bare metal deployment is also good because we might need it in the future. But it's just a way to be more flexible.
Thank you.
Okay? So, another one.
You mentioned looking at a SRO-V and DPDK. In this context, I'm wondering what interconnect are you using at the moment? Are you using Ethernet, something else? What bandwidth do you have in the interconnect?
We're using just OBS. Does it answer the question? Sorry, say that again?
I was more wondering about the physical network.
The physical network is quite simple. So the compute node just connect to a Mellanox switch, 25 gig, and that's it. It's all Ethernet, sorry. Yeah, we don't run InfiniBand or anything like that. It's all Ethernet. Ethernet, the switches are 100 gigabit per second. But to the host, we take 25 gig.
Okay, thank you.
Welcome. Okay, I think that's it. Thank you very much.